Now to thermochemistry, and the reference is to the Zumberdahl College Chemistry textbook, Chapter 6. Thermodynamics is the overall study, the science of the relationship between heat and other forms of energy. Thermochemistry is a subset of thermodynamics. It's the study of the quantity of heat that's taken in or given off by chemical reactions and other changes like that. First, we need to consider energy and work. Energy is the capacity to do work or to produce heat. We have an intuitive understanding of what energy is. We know that energy can be converted from one form to another. For instance, if you have an electric power station, it might be burning natural gas or coal to produce steam. The steam used to drive a turbine. So now you have mechanical energy, which can be harnessed to a generator to perform the task of converting to electrical energy, which powers our various appliances and lights. Energy can neither be created nor destroyed. When it's changed from one form to another, it continues to exist. The sum of kinetic and potential energy in any system is constant. And we can show this with a diagram. Over here we have a dam that has just opened the spillway. The lake behind it represents, for this parcel of water, a certain amount of potential energy. No kinetic, no energy of motion. Here, a short time later, maybe seconds later, the water has taken on kinetic energy because it is moving. The potential energy of that parcel of water has been reduced, but it's now kinetic energy. Here the kinetic energy has increased further, and the potential energy of that package of water is reduced. And here the potential energy of that packet is all gone. It's all turned into energy of motion, which you can hear as it splashes on the rocks at the bottom. Work, heat, and temperature. Temperature is not the same as heat. Temperature is not the same as energy. Temperature is a measure of the kinetic energy of a system. Heat is the energy transferred between two systems at different temperatures that are in contact with each other. For instance, if you have an ice cube in your hand, then the heat is coming out of your hand and going into the ice as it melts. Work is expressed energy, and it's defined as the force that's acting on an object over a distance. Work is equal to force times the distance that the object moves. Now, if you look at the definition of pressure, you can see that since pressure is force divided by area, work can also be expressed as the pressure on, say, a cylinder or of a cylinder of gas times the change in volume as it expands or contracts. Now, what is a state function? Well, a state function is a property that depends only on the present state, not on how it got there. So, for instance, if you're standing on the first floor of a building next to some stairs, and you move to the third floor, the energy difference between the third and the first floor is not going to matter how you got from the first to the third floor. Energy is a state function. But if you walk down the hall to the end of the building and take the stairs going up there and then come back to the position above where you are on the first floor, you have done a different amount of work to get from position 1 to position 3, first to the third floor. Work then is not a state function. Let's look at an example of system and surroundings as you read in your textbook. For instance, this is a reaction, it's a very simple reaction, burning carbon, like coal, in oxygen to form carbon dioxide. We call the coal burning in oxygen, forming the carbon dioxide, a chemical system. And around it, you have air, you have a furnace, you have ducting, they have a house being heated by that burning coal. The surroundings then are everything other than the coal burning in the oxygen to form the carbon dioxide. Now, here energy is flowing out of the system, out of the chemical reaction into the surroundings. We say it's exiting the system. We call this then an exothermic process, an exothermic chemical reaction. On the other hand, this physical change, water, ice in a solid state, water in the solid state can turn into water in the liquid state. That melting ice is a physical system, and the room that is being cooled, or your hand that is holding the ice, we would call the surroundings or environment. Here, energy is flowing out of the surroundings and into the physical system. It is entering the system, and so we call this an endothermic physical change. Now, symbolizing changes is important. If the energy of a system increases, we symbolize it as a movement from left to right and up. Energy is increasing. If the energy of the system is decreasing, we symbolize it as a movement left to right and down. So here the energy before the change is greater than the energy after the change. In endothermic processes like this one, the kinetic energy of the surroundings is going down, the temperature will go down of the surroundings, and the potential energy will increase. So we start here with ice, and here we have a higher potential energy in the water, liquid water, and the process has been driven by heat coming out of your hand into the ice. In an exothermic process, potential energy goes down and kinetic energy increases. Here, the coal and oxygen, for instance, has a higher potential energy than the carbon dioxide, and it's lost all of that to heat up the environment to make the kinetic energy of the surroundings go up. Example: why don't you discuss with your friends the kinetic and potential energy changes when you put an ice cube, there's your melting ice system, into hot tea. Also, the effect of putting a piece of food into a skillet and turning on a fire below the skillet. The gas burning now is a chemical exothermic system. Describe that and then turn this video back on. The internal energy, E, of a system is the sum of the kinetic and potential energies of all parts of the system. The energy, internal energy, can change. So the change in internal energy is going to be equal to Q plus W. Q is the heat that's added or taken away from the system. W is the work done by the system or on the system. We now define what's called enthalpy, or enthalpy if you prefer. The enthalpy H of a system is the sum of internal energy and the pressure volume product. It is a state function. Here, enthalpy, internal energy, pressure volume product. So, any change in H, delta H, is going to be equal to a change in internal energy plus, at constant pressure, that pressure times the change in volume. That's the enthalpy change. But at constant pressure, Q is the same thing. So the change in enthalpy is going to be equal to the heat of change in the system. So for a chemical reaction, the change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. And in fact, in all of thermodynamics, we're always looking at whatever we're measuring of the products minus whatever we're measuring of the reactants is the change in that particular property. You will often see thermochemical equations and you will write them. A thermochemical equation is one which shows the reactants and products, like any chemical equation, and also the enthalpy change. Example: you can show the burning of carbon in oxygen to form carbon dioxide with a chemical equation like this. You can also show that it produces 394 kilojoules by showing the heat produced as a product. The more common way of showing it, delta H, however, is the chemical equation is written first, and then we show delta H, the change in enthalpy. And in this case, since it's exothermic, delta H is a negative quantity, negative 394 kilojoules in this case. We then call this, since this is a combustion, we call this the molar enthalpy of combustion. This is a diagram of what we just did. And you see now the 394 kilojoules is coming out of the system as the potential energy drops, going from the reactants to products. Here are two important rules for manipulating thermochemical equations, and with this we will end this segment. When a thermochemical equation is multiplied by any factor, the value of delta H for the new equation is found by multiplying the delta H in the original equation by that factor. So for instance, if we were burning 2 moles of coal, then we would double the negative 394 kilojoules to get the enthalpy change. Also, if you reverse a chemical equation, the value of delta H is reversed in sign. So an exothermic equation, when you make it an endothermic equation, you change the sign of the delta H. For example, consider the reaction of methane and oxygen at constant pressure. Given the following equation, how much heat could be obtained by the combustion of 10.0 grams of methane? Here's your equation showing that delta H for the burning of 1 mole of methane is negative 890.3 kilojoules. You can see why methane, natural gas component, mostly methane, methane is such a popular fuel. So we take the 10 grams of methane, we multiply it by the reciprocal of the molar mass. 1 mole is 16 grams. We're now going into the mole hole. And when we have the moles, we then multiply it by the enthalpy change, 890.3 negative, and we get negative 556 kilojoules. So you always go into the mole hole like this. Then you're going to multiply it by the enthalpy change for 1 mole to find out the enthalpy change for that particular number of moles you're working with. This is the end of part 1 of our thermochemistry slides.